all ready. Oh, we are going. I don't know how the sound is going, but whatever. So, Mace Finger is here. Welcome back. And today we are going to. I'm going to talk about a little bit about PID tuning and all this kind of stuff. And mainly because I'm going to make myself a bit bigger because I'm going to like throw it calm. So whatever. So basically, we are going to be PID tuning the blower, which is going to be an introduction thing because I want to learn this and I want to document it for myself later if I forget it, and for the viewers can like benefit from like looking this back. So basically, this is going to be kind of like a documentation, but I'm going to stream this so that I can like look it back, and you can those who watch the stream can like see how much I was struggling and what it takes and all this kind of stuff. So this is going to be the behind the scenes clips for the breadcrumbs later to like return back when I will be older and looking back this shit if I will, I don't know, whatever. So point is, first going to talk about like, I'm going to like turn here to the ChatGPT side. I know I'm not an expert. I have learned this a long time ago, probably like 1.5 years ago. So basically, like, don't look at this, look at me. So first, why do we need this? I mean, to be honest, I will just show you. Just going to tap here, and basically this is the blower here. You can see that it's just unlucky here, so don't worry about that. So here's the blower. And why do we need this? Because the blower is a steady state thing, meaning that, I don't know if you have followed the journey or whatever, but I'm going to tell you that we have first, or I might just go to the paint section and just draw a little bit, but I don't know, whatever. So I'm going to like gesture here. Main point is that we have the blower, which is a dynamic system, meaning that it has so let's go from the beginning. So I'm just going to paint 3D apparently because they have for some reason made the old version like die. So basically we have the blower, which is a system. Let's make a little boxy. It's not going to be the most like, oh my god, this is so exciting, but it is going to be exciting if you want to learn about things. So it's kind of like engineering. It's not always like flashy and all this kind of stuff. This is what is required. So suck it up, folks. So whatever. So we have this box, which is the blower. We're going to use like this blower. So basically, to the blower we have some sort of input that they usually call U for some reason, I don't know. And there is an output which they call Y. So Y. This is basically just meaning that there is an input and there is an output, meaning we do something with the blower, we somehow control it, that's the input, and there is something output of the blower, which is air. The input is PWM. If you don't know about that, this is disgusting. Should we? So this is PWM, which is basically pulse width modulation. You need to imagine it as like a tap. If you don't know about it, whatever, you can skip ahead, but like I'm going to explain quickly. So basically you have a tap, and then it's kind of like opening the tap. If you want to control how much water goes out, you can open the tap, but it's not really useful because too much water goes out. But if you only want to like, let's say if you fully open the tap, there is 10 liters per 1 second. So in 1 second 10 liters falls out. But if you need like 5 liters per second, of course you are not going to like how to say this, you are not going to like open the tap fully. Unfortunately in electronics you can't really like just 50% open the tap like in like with water. You need to like quickly open and close the tap. So basically it is open half the time, and basically because it is like 10 liters and 5 liters, which is half if you do the math quickly, you need to open it half the time and you need to close it half of the time, and basically that is PWM. Like there is a high signal when that you send out the voltage, and there is a low signal which is 0, which basically means that the circuit is closed, and the circuit is closed when you basically send out the voltage, whatever. So the circuit is open here, basically it is not connected, so it is 0, there is no voltage. And basically there is 12 volts, which is the max, and there is 0 volts, which is the bottom. And basically there are like little whatever. So basically, don't go about it that deep. Meaning the whole thing is that you quickly open and close it, and how much percentage it is close to how much it is open. So basically, if you have a given amount of period, let's say 10 seconds, you open it once for 1 second, then close it for 1 second, open it for 1 second, close it for 1 second fully. That means it is open half the time, closed half of the time, meaning that is 50% of the amount is going to come out, meaning that it is 50% PWM. PWM, of course, in the real life doesn't happen like that. It happens based on the logic, but it is a bit more difficult and specific, and it happens a lot. So basically like 20,000 times or 50,000 times per fucking second, which is a lot. So that is why they call it 20 kilohertz, which is basically you want to operate it above like 21 kilohertz, because that is the audible range. Basically you don't hear the motor whine when you do that. Basically if you do it under that, it can still work, but it will make this noise and it will be annoying, to be honest. So usually doing about like 21 k hertz, so kilohertz, which is 21,000 times per second or more. That is the open close. This is very fast, like, yeah. So basically that's it for the PWM. Why do we need that? Because we want to control the blower, meaning that we want like not always 15 liter per second air. We need like 10 liters per sec or 12 liters per sec. But we only can do that with like a MOSFET, which is the tap in this case, and we can control that with a we'll see. We'll show you the STM32. By the way, it's called the R446 or F446RE. By the way, he is the guy. Just this is the G. If I can bring up a fucking picture of him. Here's the guy. He's like a microcontroller. So basically he can do a lot of things, but mainly for the purpose, he does the PWM, which basically is done by like you type the code in to his memory, and then he basically does that, and you can like control it. I do control it through MATLAB, which basically I send him like commands, and then I can adjust the PWM as between 0 and 100%, of course. So yeah. And PWM is the input, and the output is going to be liters per sec, or it is to be more appropriate to call it volumetric flow, which is in dimension liter per sec, or delta P, which is the laggy shit. So delta P, which is differential pressure between the, so basically, so there is the to stand up. So basically here we have the this makeshift 3D printed orifice plate thing, which is here the orifice plate. Basically it works like that. There is differential pressure here. Basically there is a restriction, and there is going to be, you know, pressure drop between here and here. So here the pressure is lower than here, proportional to the amount of air that goes through. If 5 liter per air goes, or 5 liter per sec air goes through, there is like 1 amount of pressure drop there. If 10, then it is 2 there. It basically is linear. So if I remember correctly, or quadratic, I can't remember, maybe quadratic, whatever. So there is like a relation between volumetric flow and the delta P there, and basically the delta P between the two lines, so this and this, is measured by a pressure sensor which hangs there, just completely garbage design, I know, just, you know, it's just temporary, so whatever. And basically the delta P can be converted into volumetric flow. That's the point of the whole thing. So yes, so yeah, that's the output that we can read, and this volumetric flow is the output. So why do we need all this nonsense, whatever? So basically I have measured out the input, which is PWM, and how much volumetric flow. So basically, that's like a steady state thing, meaning that it is like a, how do you say this? In general. So basically, if I set 80% PWM, is going to be 12 liter per second. It's going to be a bit, you know, fluctuating because of the pressure, noise, and all this thing, but it's going to be fluctuating around that. So the point is that this is all great, but what if, or what happens when I go from, let's say, 50% to 70%? Because in that, I don't know, we don't know yet, but let's say there is 5 seconds which the pressure goes like this, or it can go like this. Who knows? No one knows, because I haven't measured. So we need to measure that. We need to determine, because this is called the dynamic state. So that is why they usually write the, I'm going to make it even smaller. That is why they usually write here T, which means that it is dependent on time. So it is a function of time, meaning that it is dynamic. So it changes with time, and it is like the steady state without T, or like that thing, is basically after here, the, like here, this side, which is basically like what it settles to. But we are also interested in what happens here, because that is important, because the flame is like a dynamic thing. You need to like control it properly. If you increase the pressure, if you increase the blow air, meaning like the amount of volume of air that goes in, you can easily blow out the flame, and then it's gone. You need to be you need to know exactly how you need to adjust the fuel pump, PWM. That's the same thing with blower. So basically, you need to increase them, you know, kind of proportional to each other, meaning that if you don't know this, meaning the if you don't know how much the pressure, or like how the volumetric flow behaves in time, then you might, you know, have some trouble later, and you can cause a lot of trouble with that later. So that is very dangerous, because in the, you know, burner there can be like a explosion because of the flame out. So basically the flame goes out, the propane gas still is in there, the fuel is getting sprayed across the liner inside, and then just the heat from the liner will just ignite the flame, or meaning the gas inside, or the liquid fuel inside, which is hot, and then it's just going to create an explosion, and that can fracture the whole hull, or create a detonation, whatever. It can like cause serious problems. So this is not something to take like lightly. I mean, here with the blower it's pretty like safe, so that is why it is chosen for as like a PID introduction learning curve thing. So that is why I do it. So I have researched this with, like, I have read a little bit about it before I start preaching bullshit about it, just like YouTube folks do, to be honest. So basically, the whole point of the whole system is there are like multiple things that we can determine, and these are like there is Control A, going to delete this. So basically, there is a whole thing of behavior that we can describe. There are multiple types of systems on how they respond. So there is this thing called come here, first order model. Basically, there is no dead time here, meaning that we'll show what it is. So basically, we need to imagine two lines. If I can find myself a line. So basically, here we have these two axes, and we are going to have this y-axis and two x-axis. I mean, two y-axis as well, but like you get the point. So basically, here we have the y, which is going to be pressure delta P. Well, let's make it volumetric flow, whatever. Volumetric flow here is the commanding signal, so PWM. So this is not the given like what I told you is the on-off, but the actual thing that, let's say this is like 50%, and then here is like a jump, and it is going up to like 70%, going to make it like all the way. So this is 70%, this is 50%. There is like a step response, as they call it. So basically, here's the volumetric flow, which is based like this, like it's going to like be. This is kind of realistic. You know, my hand is shaky, but like that is kind of realistic how it looks. It doesn't look like a flat thing. This should look like a flat thing, because this is constant, this is not. So basically, this will have some sort of like response. It goes up like that, and then it stabilizes and it fluctuates around that. So yeah, and even it can have like a little bit of like drift. This doesn't have a drift. So basically, what we can determine from here is that we can look here. This is called the dead time. The oopsie. So this is called the dead time. Basically, when we apply the PWM signal, and when actually something happens in the system, in the output. So that is the dead time. This is the tau. I'm going to be signaling that. So this is the tau. This is this. Where are you? So this is the tau. Where is this? So or oh, sorry, no, this is not tau. I'm changing it like that's why. What? Sorry. Whatever. Looks terrible, man. Whatever. This is called the L or L or theta. I don't know how they call this. L, theta, whatever. So this is the yes, this is the theta. So basically, like yeah, the command change and the rise or the decrease. It could be as well. So yes, this is L. The what I thought is the theta, which I don't find, or the this. Where the fuck are you? So time constant. So the time constant is going to be basically, I fucked it up. Sorry. So that's why we check. That's why we do this. So basically, we have the baseline and the this guess shit, whatever. So basically we are going to like 63 point something percent of it. 63.2% I think is the given amount, so we need that, which is going to be about here, let's say. And this basically from I think it's going to be from the here to here. So basically this, let's use it green. I think this is it. I will have to check this, but like I think this is it. So basically this is going to be the L or the theta. This is theta. This is the L, which is that time. And there is also like a another thing which is called like where the fuck are you? Rise time, which is TR. I don't know what that is used, but like whatever. So that's supposed to be like 95%. Let's say where are you? Let's say purple. So basically from 90% or like from 10% to 90%, this amount of time, which will be the TR, which God knows who uses or but whatever. That is the thing, whatever. So yeah, we can take these. The main concept is you can look it up. It doesn't matter if I tell you in this video, like always double check like these things at least. Whatever, uncertainty. So basically we'll refine this, but like the main point is that you can take down these or like read these constants from the actual response. You do these step responses. Let's say I have this blower going from 50 to 70, or like 60 to 70, 65 to 80, whatever, 80 to 50. You can also look at the asymmetry. So basically, how does it react in like going backwards from like 80 to 50, or like rather than 50 to 80. So yeah, that is also a good thing to look at. But here you can basically like create these little plots, and then you can like determine these constants. And what are these good for? You basically can create a model with them, mathematical model. You basically have this thing called the transfer function, which can be like derived from here, from like graphics, and can derive from like physics. If you have the equation of the physics, so basically if you have like a spring or like a dampener, you can basically put together these in like, you know, physical things, but it's going to be creating like a equation, a physical equation. Then you need to Laplace transform that, because this transfer function is Laplace transformer, or like a Laplace transformed thing. So basically I'm going to show you. Here it is. So the first order model here, GS means the transfer function, and S means that it is like the, basically if you take something that is in the time domain, which is just normal thing, that is f, or the what is this called, the function of t. But if you Laplace that, that is going to be the function of s. I don't know the mathematics behind it, but you know, only to this know this. So basically here we have again k, t, this tau, which is supposed to be the I mean, like time constant in problem with the names. So whatever, how long it reaches the like 63.2% of the total, like the total gain change. So that the S doesn't stand for jack shit, so leave that. So it doesn't really matter. It's just the sign that it is Laplace transform, because you need to like Laplace transforming means that you need to like times things with like S. So it's some things are going to like whatever. You can look at like Laplace transforming if you are interested. This is not going to be like about this. So yeah, it looks like this, but probably this is not going to be like that. This is the other version. This is the plot, and then from the plot you can like put together the transfer function, and then you can use that to make the controller. So why is this good again? Take the physical thing, measure it with step responses, then you have a data points, then you can plot them, you can determine these constants, then from the constants you can basically create the transfer function, as well as like you can use the these constants to tune. So basically create a controller that's called a PID controller, P proportional integral derivative term. So they can be like 3, there can be only like P, PID, PI, PD, DP, and all these kind of combinations, ID, but those are not like that really common. PI and PID, those are like more common. They don't really like the D. It's hard to tune, if I heard it correctly, but whatever. So what does each stand for? And I mean, first, why it is good. So why it is good is because basically, as we talked about it, you know, in time it fluctuates, meaning the output. The input is constant, the output can change. You know, the temperature goes down a little bit, then the volumetric flow increases, or the temperature increases, then the volumetric flow down goes down, because you know, if you run something for a long time, it can like cause this, and there like a little debris goes into the fuel pump or something, and it needs to like work extra harder, because like, or like it decreases the volumetric flow of the pump, so it basically like lowers the whole thing. But of course it should be like cleaned out after a time, but you don't want to clean it every single day. So you, let's say you stop the thing after like, I don't know, 3 days or 4 days of runtime. So with like big plants, they usually don't like shut it down every single day. Usually it's like continuous, and then they, you know, have like some days when they need to like, or at the end of the day they shut it down so that they can like do maintenance on it, so that way it can, you know, there is like a room that the controller can adjust it between. So of course when it is like absolutely like shutting down because it's some malfunction, it's not going to like increase the shit out of the, let's say, fuel amount if it is fully like clogged. But if there is a little bit of clogging and it still can like, you know, push it towards, you know, it can increase the PWM because it like sees that the, let's say, the temperature changed, therefore the amount basically like the viscosity gets lower and it pumps more fuel, which is not necessary, so it will lower the amount of PWM, and then it basically has the exact same amount of fuel and the exact same amount of air, and it basically does that with the air as well. So it can basically do this, and if it is fluctuating, it can adjust it a little bit, not too much, probably like 10 or maybe 20% ish, but that is significant in terms of the output, because you're not getting like a shit flame in this instance, which is basically like very inefficient, meaning that it has very like lower, like 10-20% lower, or maybe even more heat, like calorie, meaning that work, heat, energy, whatever, that is done, because the, you know, flame is very like sensitive to these little changes. That's why, you know, it is important to like do the excess air and all this kind of stuff, you know, we set these things accordingly. You know, there are like emission things as well, but like point is that you need like in time you need to adjust the thing, and in like 10% for the little fluctuations in time, because, you know, what, I don't know, pressure change can happen, or like temperature change can happen, all this shit can happen, and we want to control that as well. And for that we create the controller, but we calculate it from the constants that we derive from either the physical model or from the plots. And that is not done by us because it is kind of like hard, because you need to tune two things at the same time, so it's kind of like an iterative method. There are like multiple things for it to like check, but Cohen-Kuhn is one, Ziegler-Nichols is another. I don't know the other names. There are multiple things. So basically, like, I'll find it. So basically, there are these things. This is the control function. That's why they say, and there are all these things that you can like derive. So I mean, I don't know where it is here. So basically, here is the this is the I think it is called the first. That was the first order. This is like a second order, or I don't know, delayed. I think delayed first order. That's the name of it. Don't quote me on that. So basically, this is like an offsetted one that needs, you know, this basically has like some sort of like delay. So this L is here, that time that we talked about. So, you know, it contains that, and you need this the integral term, meaning the proportional is going to be proportional to the change needed. The integral is basically like if you overshoot by a little or undershoot by a little, you know, it takes these terms and it basically like adds to like a memory to itself, and basically based on the memory, if, you know, there's still change, let's say you have like a volumetric flow of 10 liters per second, you add the proportional gain to it, and it basically overshoots by like two let's say 0.5 liter, and you know, it fluctuates because it overshoots it, or then undershoots, overshoots, undershoots, because it increases, decreases the PWM, but it never will reach the desired volumetric flow. Therefore, the interval, which basically has like a memory, that will, yeah, here's like +5, here's -5, and then it basically like adds these together, and then it is going to like, you know, proportional to the memory, it is going to like decrease or increase. Basically, if there is like constant over, you know, then it is going to be basically like decreasing the PWM a little bit, and then it is going to wait, you know, and it is with time, with the data decreasing, it is going to decrease the integral term as well. So it is going to you know, go towards the line. It is of course never going to like totally like be equal with it, but it's going to like very near going towards it, like more than with just the proportional term. And there is also the derivative that is done by like, you know, you have like what derivative is like, therefore is that you have like a function. This is in terms of like the response, basically has like some sort of how do you say this, steepness basically. The more steep the thing, the bigger the derivative gain is, meaning that if you have like starting to increase the PWM from 20 to 70%, the output will go up, shoot the fuck up. Then, you know, the derivative will take that as like a very big thing, so it will counteract that. So that's why the negative feedback is when you have this, like will show, but you have this feedback. So basically you have the input, the controller, and then you have the thing, meaning the physical model basically that you control, and then it has an output. The output, you know, goes out, and of course it goes back. It has like this feedback, but it is negative, so therefore the derivative gain is like then you know, subtracted, that's the word. So subtracted out of the PWM, which the controller will send, and basically it is round back. So basically as the steepness decreases, so does the derivative term gain go down, like derivative term gain, yeah, goes down. So basically as it's basically like flattens out, the derivative term shrinks down as well. So that is the PID terming. So yeah, you can use like all three hopefully, and then that is the best case, but not always, like, you know, but PI is like pretty much good for a lot of things, but not everything, as like in most cases in life. So basically sync, I haven't even heard of these, to be honest. I have heard of the Cohen-Kuhn and the Ziegler-Nichols. There are a lot of like tuning styles. You know, there is like one thing that I think MATLAB, basically we can use like MATLAB, which has this thing called like the PID tuning, and it finds these constants and all this kind of stuff, so it's pretty fun. But I think it uses Ziegler-Nichols or Cohen-Kuhn, I can't remember, whatever. So the point is, it finds you good things, but we will do it without that as well. But you can adjust the robustness and the responsiveness. Basically, robustness means that to how big of a jump does it need to like respond. So basically, if something is very robust, then, you know, a big jump will only be like I think I can't remember, but I think the responsiveness is that how big. I think I'm mistaken it, but I think the responsiveness is basically how small of a change in the pressure or the volumetric flow will you know, activate the controller to use the PID and all this, because there is like a baseline, you know, because of the fluctuation that, you know, we don't give a shit about if the pressure is going down by a little bit, and then you don't want to like, how to say this, like over constrain it, but like always running with the PID, you know, controller. If it is not, you know, out of a zone, like a significant zone, then we just don't even, you know, turn that off on. I mean, it is, you know, run by like an internal thing, so we don't, you know, control that, but the main point is that. So it just turns on when, you know, the fluctuation is out of a certain limit, or like a dead band, whatever. And yes, that is the responsiveness. So basically and that can be a bad thing as well if it is like, you know, because, you know, it takes some time. So basically there are like slow systems, like thermal systems, which are basically like you start going up, but it isn't like increasing that much. But if, let's say, when I had like a previous project that was like a tube, and it had well, draw it, I think that will be a bit more intuitive, let's say it that way. So basically I had a tube, this is garbage, so I had a tube, or whatever, had a tube, and you know, there were like catalyst things in it, these are little beads that have coated with like catalyst. And I had a what is this called, a heating element around it, wrapped around it. So basically it was heating up the thermal quartz tube, and through the quartz tube it gave the heat to the balls or beads. And basically when you turn the thing on and you basically put like I'm saying basically too much, sorry. So yeah, we have a thermocouple here inserted, and it is guided through here, outside, whatever, and we measure this. When we turn on the thing, if we don't have it like too responsive, we turn it on, the temperature is a lot, like there is a lot of dead time between when it happens, meaning the heating happens, and when the heater actually is turned on. Basically I turn on the heater, temperature is still, but when the temperature starts rising, it doesn't stop when the heater is stopped. It is going like through the roof. And that's why responsiveness in that instance is very important, to that little responses. Even it is like hard cutting it off, because when it starts to rise, it is already almost late to turn it off, because it will like run out of the band that you want to keep it in. So yeah, that is the kind of like the counter argument against like responsiveness. So there is not like a good or bad answer to like either robustness or responsiveness. I think robustness is about like keeping the value in a given zone. That is robustness, I think. So no matter how much you outside signal, let's say you decrease the temperature by a lot or like increase the temperature by a lot, you still have the same zone, and it is basically the completely robust system is just irresponsive of the external inputs. That can be good, but then you would basically like zero out the responsiveness, meaning that the response needs to be basically zero to every single interference. You need to put the response. So basically like they are bad with these words, but like counterintuitive or like diabolical, whatever. So they are like if you increase one, then the other will go down. So if you increase this, that other will go down. So they are kind of like opposites, and to some extent you can like increase them both, but at some point you are going to lose one to the other, to the sake of the other. So it's kind of sucks, but as again, there is no good or right answer. There is a good answer or like a good enough answer to a given system, or that's how it works in reality. So rant or like side point ended. So yeah, I have told quite some about this. So what will be done about this is that basically like I will do this thing of first sorry, my mind went blank a bit. I'm like kind of like coming off of like university thing and like kind of burnt out and like pretty brain dead at this point. Point is that what I'm going to do is that first of all going to figure out some plan, meaning like what levels, so let's say 60 to 70 and so on, PWMs we need to like jump from, and how much, and then we are going to, or like I'm going to be honest, create like plots that I have shown, and then from the plots we are going to determine if the current sampling time, meaning like 2 hertz per sec, 2 hertz 2 hertz per sec, so hertz is meaning like 1 per sec. So hertz is that 2 hertz is that basically every single second there is like half 500 milliseconds, so half a second between each measurement of pressure. And if that is like good enough, because we need like 10 to 20 seconds when the increase in like volumetric flow or delta p, whatever. If it is like in 1 second, meaning like it is like this, like goes up to the steady state, then it is like not adequate, meaning like we need to increase the sampling size, sampling time needs to be decreased to it is called the I think sample rate. Sample rate needs to be increased or sample time needs to decrease, so that we basically can see, because if it is like this, then no one knows about jack shit, because it is too steep to like determine the time constants and all this kind of stuff. You really need to like pull the diagram out, meaning like we need to increase the frame per second, or like in this instance the sampling rate per second, which is measured in hertz. So yeah, that will be done, and after we have determined which is the right, if we can stay or need to change the sampling time, then going to do the given constant determination, and after the constants are like determined, then we can calculate the PID control terms. They are called terms. So the P and I and all this kind of stuff, terms, I mean, yeah, sure, they are only this. Hopefully we could technically do a D, so derivative term as well. I don't know about that. So we will, depending on also how the model responds, because if it goes over, or like if it immediately starts, like there is no dead time, then there is a first order thing. If it is going after it, after the response, or like the PID is adjusted, then it is like a first order with the dead time. So we need to determine that as well, and then based on that we can create the controller terms, and then create the controller with tuning, and then test it. That's going to be the plan. So yeah, that's it for today. Thanks for watching. Do the hard work, especially when you don't feel like it.